Hey friends, welcome. Today we are again going to discuss the Nernst heat theorem. This was my first video on YouTube and the audio quality as well as video quality was not up to the mark, so I have decided to make this video once more. And also I would like to suggest me few of the topics which you want from me so that I can make videos in the future. Beginning with the Nernst heat theorem. This theorem was basically given by Walter Nernst, and this was out of several observations. And whenever we are studying the third law of thermodynamics, the first thing that we encounter or the first thing that we study is the Nernst heat theorem. And this heat theorem, or it is called Nernst heat theorem, basically because we are taking the heat out of the system. So we are taking the heat out of the system, and as a result the temperature of the system is decreasing, and as the temperature of the system is decreasing, the temperature is going, or the temperature is tending towards the zero, and hence this particular theorem is known as Nernst heat theorem. And this theorem has its basis from the Gibbs-Helmholtz equation. So the Gibbs-Helmholtz equation, we all know it very well, that is, it is given by delta G is equal to delta H minus T d delta G by dt at constant pressure. So this is our Gibbs-Helmholtz equation, and over here delta G, we know it is the change in the free energy, delta H is our change in the enthalpy, and d delta G upon dt, it is known as Gibbs function. Okay, it is known as Gibbs function, and at absolute zero, so whenever we are considering the temperature T is equal to 0, at that time delta G will be equal to delta H. Now Richardson, he calculated the EMF, or he observed by calculating various EMF values of different cells at different temperatures, and he observed that this value of Gibbs function, it is decreasing as the temperature is decreased, and therefore he concluded that the value of delta G and delta H, they approach each other more closely as the temperatures are lowered. And relying on this generalization, or relying on this data of Richards, Nernst, he postulated, or he gave the Nernst heat theorem, and the Nernst heat theorem, it states that the value of the Gibbs function, it approaches zero as the temperature is lowered towards absolute zero. So as the temperature of the system is lowered towards absolute zero, the value of Gibbs function, that is d delta G upon dt, it also approaches zero as the temperature of the system approaches zero. And this particular statement is known as Nernst heat theorem. And according to this theorem, over here, when T tends to 0, then this value will, or Gibbs function will tend to 0. Under such circumstances, the value of delta G and delta H also may, or they are not only becoming equal to each other, but they are approaching each other gradually as the temperature is closing to 0. And this can be explained by taking the plot of delta G, or say delta H versus temperature in Kelvin, and it is observed that the change in the enthalpy, that is delta H, increases and it reaches at a point at absolute zero. So this is our zero, and similarly the value of delta G is also decreasing and approaching a specific value, and at absolute zero, value of delta H will be equal to delta G. So this is our Nernst heat theorem, and mathematically we can write a Nernst heat theorem as limit of T tends to 0 d delta G by dt at constant P is equal to, I can write limit of T tends to 0 d delta H upon delta T at constant pressure, and that is equal to 0. That is as T tends to 0, we can say that the Gibbs function is equal to the change in the enthalpy with respect to temperature, and that is equal to 0 at absolute 0. So this is the mathematical form of the Nernst heat theorem. And again, we know that from second law of thermodynamics that the change, that is d delta G by dt, is equal to minus delta S, and similarly d delta H by dt, it is Cp. So this is our Kirchhoff's equation, and this is the change in the entropy of the system. Okay, this is the delta S is the change in the entropy of the system, and this is the heat capacity at constant pressure. So both these values can be used in this relation, and hence I can write limit of T tends to 0. I can write delta S is equal to 0, and limit of T tends to 0, Cp is equal to 0. So these are the two consequences of the Nernst heat theorem, and the detailed lectures on this I have pinned it in the comments, so you can see over here. And this signifies both this equation signifies that the entropy change of a reaction, it tends to approach 0 at absolute 0, and similarly the difference between, this is delta Cp, okay, this is delta Cp. So the change in the heat capacities, or the difference in the heat capacities of the product and the reactant also, it tends, or it approaches to 0 as the temperature of the system is lowered. So these are the two consequences from the Nernst heat theorem, and this theorem, or the Nernst heat theorem, it holds good only in case of pure solids. It cannot be applied in case of solutions, or in general gases case. And Walter Nernst, he was awarded Nobel Prize in 1920 for his work in thermochemistry, and also he has pioneered work in electrochemistry also. In electrochemistry also we studied Nernst equation, so that is basically derived by Walter Nernst. And the statement of third law of thermodynamics, we know it very well, that is at absolute 0 temperature, the entropy of a perfectly crystalline solid, it is always 0. So this is the statement of third law of thermodynamics, and it was basically because of the Nernst heat theorem. Okay, hope the explanation is more clear now. Thank you very much for your help and support.